Hello, everyone. Um, Welcome to the Transitional Artificial Intelligence Research Group seminar series. Today, we have Yuhao Ke, who is a Master's of Data Science student, and he is about to complete the program. And one of the parts of the Master of Data Science program at UNSW by coursework is you do a 2-trimester thesis, which is around 7 months. And Yuhao has come up with this idea, and then we met and discussed it further, and it became this project basically. And so today, I am very proud to say that Yuhao has published this in a journal paper, and that is Applied Soft Computing Journal, which is a leading artificial intelligence journal in the field. And Yuhao is hence providing this seminar to give further details about his project. Thanks, Yuhao.
Thank you. Hello, everyone. I'm Yuhao, and this is our paper, a unified machine learning framework for the basketball team roster construction for both the NBA and WNBA. And before we start, I want to truly thank to Rocket Changer and WNBA. Thank you for all the help for me. And let's start. So first, let's introduce some background. So the National Basketball Association, NBA, is the professional basketball league in North America, and that has 30 teams, is considered the premier professional basketball league in the world. And that's the association. And in NBA, remaining competitive is very essential. And this on the screen, you can see the team Golden State Warriors. They are the most successful team in the past decades. They won the championship 4 times from 2015 to 2022, and their revenue raised from $450 million to $5.6 billion over these years. So if you are very competitive team, you can earn more money. That is very simple in NBA world. And if you want to stay competitive, you have to pay a lot of salaries to the team members, right? And in NBA, there's a very unique system called salary cap and luxury tax. That means if the over payroll of the team members exceeds some number, you have to pay some fines, which is the luxury tax. This is the screenshot of the luxury tax for the teams, the top luxury tax in this year. And the first one is LA Clippers. That is a very successful team. The payroll is to about $200 million, but they have to pay the luxury tax fees. That is about $155 million. That is almost as high as the actual payroll. So that is very large, right? That is a very large luxury fees. And our goal is to design a machine learning framework to help the team manager in the NBA to choose the appropriate players to remain both competitive and while not exceeding the salary cap. And here is about the literature. We are going to review some existing literature. So first is about supervised machine learning. And they are very commonly used in the prediction of NBA models, and they mostly focus on predicting the outcomes of particular games. So they are focused on some particular games. The unsupervised machine learning, they are widely used in sports research, not only in the basketball, they are used in a lot of basketballs, and they are basically focused on the player categorization. And in detail, for the supervised learning, so we can find, I should change this actually. So for the supervised learning, they found that the supervector regression, polynomial regression, and random forest regression, they exhibit very competitive capability in prediction of the NBA games. And second one, they find that ensemble learning methods to predict NBA players' future performance, and they report that the balanced undersampling random forest made the greatest best performance for the NBA All-Star election. So that is very important to note that this one is based on the prediction of the All-Star election. That is not the performance of a team, but a performance of a player. And the third one, they find that they have used a lot of cross research. They compare the field words, radius basis, probabilistic, and generalized regression neural networks. And for the unsupervised learning, so first one, they use the anthropometric, which is like height, weight, experience to group the NBA players. And the second one, they implemented a two-step clustering, identify 5 performance profiles for the regular season and 4 performance profiles during playoff games. The third one, they applied the TSNE and PCA to do the dimensional reduction and identify 4 groups. So let's do some conclusion here. So first, for the supervised learning, they are generally good, but they all focus on particular games. None of them focus on the overall season. That is the question. That's the question we need to fix. And for the unsupervised, usually they categorize them in 4 to 6 groups. The number is the issue. So if you are kind of familiar with the basketball, all the players are already categorized in 5 positions on the ground, right? They are centers, they are PF, they are SG, they are all the 5 positions. We already know that. And if you are an expert or if you are a scout for the team, when you are categorize them, you will categorize them like more than five groups. So the number is the issue. We need to have more detailed group categorization than that. So here is the table of contents of our paper. So first we will introduce a framework, then we will get to all the steps in this framework, and we will do some and we will point out some future work we can do. Here is the overall framework. So first step you can see on the yellow one. So here is the dimensional reduction. We first use some NBA player performance, and we reduce the dimensionality to get the PCA transformed data. We transform them from a lot of features to some fewer features. And the second step is the clustering. We use these transformed features to cluster all the players into some groups. And then we can label the players with their group, and we can do the third step, which is the neural network model. And this one is a trick one. We use that to build a model that can predict the overall performance of a specific team. And once we have this one, we can construct our team based on this model. And the fourth step is the rating system. We also provide a rating system that can rate the players according to their clusters. And the very last step is the team construction, the real team construction, because we need to construct team under the salary cap. We don't want the salary to exceed the salary cap. So we need to choose the best players from our desired team model without exceeding the salary caps. So that is the whole framework. And then here's a problem with the number of features. So we already point out that we need more than 5 or 6 groups. In order to have more groups, more clusters, we have to increase the number of features, right? And if we choose more number of features, that will cause overfitting, which will reduce the performance. So that is the problem with the number of features. So here's how we do. We choose more features, but we reduce the dimensionality using PCA. That is the one to do. So here's the first part, dimensionality reduction. And here's the input of the data. We collect 8,511 players. They are not the actual number of players, but because same player in different year were treated as different players. So you can see the years in front of the actual name. So that means 2,000 years of this player in 2,000 years. And all these columns are the features. And in total, we have 71 features. They are all collected from the NBA official website. And originally, we have 71 features. And then we use the PCA. And here is the total variance, total expanded variance. And here are the number of components. And you can see over 90% of the total variance can be explained by 13 components. So we reduce the number of features from 71 to 13. And other than PCA, there's also another method called manually selected. So DataATL, they show that the most rated features in basketball games are these 7 features. And the question is whether these 7 features are better or the PCA features we just developed are better. So that's the question. And here are the comparison of them. Manually selected features, they are easier to interpret because they are just the features on the official website. We know what they are. and they can reduce the number further, right? There are only 7. But the performance of these features are hard to evaluate. We don't know for sure why PCA is better or why the manually selected are better. Thus, we decide to use both methods in the data, apply them to the next step, which is clustering, and we choose those methods based on the performance of clustering. And here is a simple interpretation of PCA features. If you are familiar with PCA, you know that one PCA feature is a composition of all the features, like the 71 features, and we just need different coefficients for them. And for one PCA feature, we choose the 3 most important features. That is 3 features with the highest coefficients. And this highest means the highest absolute value, not the actual value. And we interpret the PCA features based on these important features. Here's an example of the first feature. The first PCA feature composed with these 3 important features: the total minutes, the total FGM means field goal made, and the total FGA means the field goal attempted. So that means we can interpret this one because we know that minutes, field goal made, and field goal attempted, they are the offensive ability of the players. That's how we can interpret the PCA features. And then let's move forward to the clustering. And for the clustering, in this step, we use two different methods of clustering, the k-means and the hierarchical. And for the metrics, we try out the CLS scores and the inertia. And we also do the visualization of the clusters using the PCA, TNC, and the UMAP. And here is the result of k-means. So for inertia, the best outcome of the inertia is where the breakpoint happens. So maybe in this case, is somewhere here, like 3 or 4. But this is not what we wanted. As you pointed out, we want more than 46 groups. So we think inertia maybe is not the best metrics in this situation. So we decide to use the CO8. Now, let's compare the k-means and hierarchical. So for the k-means, you can see that for the CLS score, the best one is the local maximum. The local maximum in this case is the number of 10. And here is also the number of 10. There are the local maximum. So they agree that the number cluster should be 10. And maybe for the hierarchical one, the CLS score is higher than this one, right? So maybe hierarchical is better in this case. And then move forward to the clustering for the manually selected data. And they also show that 10 is the optimal one. So also either we use the manually selected data or we use the PCA data, either we use the k-means or either we use the hierarchical, they all agree that we should have 10 clusters in this case. All right, if we choose K as 10, and we believe that because for the hierarchical, the CLS score is always higher than the k-means. So we use hierarchical and choose K equals to 10 and investigate how the manually set data or the PCA data. And here is the visualization for the PCA data and the manually selected data. The PCA data shows that here's the TSNE. Here's the TSNE visualization method. So for this one, PCA is a lot better than the manually selected data, right? They are more categorized. The distance from groups for the groups are larger than the second one. But for the UMAP, they say that they are equally the same. They are basically the same performance. So maybe we need to do a further investigation. So that leads to the actual members inside the clusters. So here are the demonstration. First one, the NBA data with PCA transformation. Here's the PCA data. Using the PCA data and hierarchical and K equals to 10, we got these 3 clusters, cluster 1, cluster 5, and cluster 8. All right, you can see that here is Allen Iverson, Kobe Bryant, LeBron James. If you are familiar with them, they are very popular players. They are very good. All right, and all these players, all these 9 players, they are all very good. Okay, and the beauty of that is that these 3 players, they share the same play style. They are basically the same. And these 3 players, they share the same style. And you can see that they are in different years, right? It's 2000, 2008, and 2022. They are basically the same. And these 3, they are basically the same. So the PCA data has clustered them in different clusters as they need to be. But the manual select data, all these nine players, they are all inside one single cluster, but they have different playing style. So then we can decide the PCA data should be better than the manually selected data. And by now, we have decided that we cluster them into 10 groups, and we use the hierarchical, and we use the CLA score. And let's move forward. And here's the conclusion for the PCA and the manually selected. And here we move forward to the neural network model. And here is the input. The input of the neural network model, they are made from the player clusters and the player time slot. All right, the player time slot means how much time each player plays overall for the season. And the output of the neural network is the NBA team seasonal results. So a team for a season is considered successful if they win the first round of the playoff. And this value is going to be 1 if they win the first round. It's going to be 0 if they do not win the first round. And after we get this neural network model change, and we can do some predictions. Use this model to do the predictions, we can know what kind of players we want. And let's go to here. Build a neural network to predict the seasonal outcome for a specific team given the field time of players. And use the trained model to determine what kind of players to be chosen. Here is the demonstration of the network. So the input, you got the field time proportion of each clusters in a team. So here you can see that we have 10 nodes as the input. And each node means the time proportion, not for a player, but for a cluster. And the output is whether the team win the first round of playoffs. And because the input could be very confusing, so let's use an example to demonstrate that. So here's the input. So here's one input for one record. Here's the input of one record for the neural network. Here is the actual Lakers roster in 2009. You can see here are the players' name. Here is the cluster they are categorized in. And here is the time proportion, right? This is not the actual time, but the time proportion they played in the whole team. Okay, and you can see that Kobe Bryant is in cluster 1, and he's the only one in cluster 1 in this whole team. So for the input, cluster 1, the input 1 is 0.148, as the same as Kobe Bryant. And for maybe cluster 6, you can see that here are 1, 2, 3, 4 players in cluster 6. And we should add these numbers up to be the number for cluster 6 in the input. So that's how we construct the input for each record. After we construct that, we can train the neural network. And here is the performance of the neural network using Adam or using the SGD as the solver. And you can see that using Adam is a little bit better than SGD. So we decided to go with the Adam in our actual network. And then here is the second step of the neural network. Now we have trained the neural network. Okay, so here's how we should use that. All right, the neural network can just tell us for a given team whether they can win the first round. All right, but as a team manager, I need to know how can I win the first round. So which player I need to choose. So here is basically how they construct a team in the real world. First, we choose the elite players. So remember, we have identified cluster 1, 5, 8, all these clusters as the elite clusters. They are all elite players. They are very good players. And normally, an elite player plays for around 35 minutes in a game. So we know the playing time for them. And we set the time proportion based on these 35 minutes. So you can see here, 35 minutes divided by 48 minutes is the whole game. And we have 5 players always on the ground. So here is the time proportion for one single elite player. Okay. So, and you can see here, cluster 1, elite player, cluster 5, cluster 8. All right, they are elite players. So the first one, we choose only one elite players from cluster 1. All right. And we know that the salary for elite players, they are usually very high. And maybe 3 elite players salary, normally they will exceed the whole salary cap. And it's impossible to get only 3 players in your team, right? So you can only choose up to 2 elite players. So only 1 or 2. Then we distribute the rest time equally to all the other players, all the other non-elite players. So as you can see, for the first try, we choose only one elite player from cluster 1, no player from cluster 5, no player from cluster 8, and the other are all the same. And then using the neural network, you can get the prediction. You can get the probability to win the first round, which is 0.427. That is very low. We don't want that, right? And then you choose only from cluster 5, only from cluster 8, and all the other combinations, cluster 1 and 5, cluster 1 and 8, cluster 5 and 8. You try all of them, and you can find that this one has the highest probability, which is around 0.5. And this one is cluster 1 and cluster 8. Right? So that means if you have these 2 players and you have all the other different kinds of players from other clusters, you are guaranteed to have a half probability to win. But that's not enough, right? That's not enough. So we need to choose specifically for the non-elite player. But we know that cluster 1 and 8, they are the best elite players. Then we choose the other players. Okay. So we choose the elite players from cluster 1 and 8, that is set, and we examine the non-elite players from the other clusters one by one. So you can see that cluster 1 and 8 are said to be the same thing, right? The 35 minutes we discussed before. And cluster 5, they are all 0 because we do not choose the elite players from cluster 5. And we examine them one by one. So this one means I choose cluster 1 and cluster 8, and the others are all from cluster 2. And we get the probability, and same as all the way down here. And you can find that the highest probability is here. So with cluster 9, we have the highest probability, that is 0.7. And with cluster 4, we also have a good probability with 0.64. So we decide to choose from cluster 4 and 9 as non-elite players. So by now, we know that we need 1 from cluster 1. We need 1 from cluster 9. We need someone from cluster 4. We need 1 from cluster 1 and 1 from cluster 8, some from cluster 4 and some from cluster 9. So that is the composition of our team. They are set. And we should move forward to which player to choose from that cluster. And that comes with the rating system. So for the rating system, we need all the NBA game logs. The game logs is just a statistic sheet that shows all the things, all the features of the team, or for a player, for each game by game, not for the whole season, but for the games. And using that, here's our system. The game logs composed of the team performance and the player performance. So we first examine the team performance. We use the team performance game logs to decide which features are most significant in the games. All right. And after we know that, we can know the coefficients to each features. Using these features, and we apply them to the player performance. And we can examine for this player, what is the coordinate features. And we times the coefficients and get a sum, which is the player rating. And for one player, you have all the ratings for different games. All right. And these are called the rating sets for this player. And we have 2 weights. One is time weights, the other is pressure weights. Time weights means if the time is more recent, that will have more weights. The pressure weights means if the game is very competitive, very tough, they have more weights. And then combine them, get the average, we get the overall rating for this player. And here is the significant features. We just use a logistic linear regression to get the significant features for the game. And you can see here, the p-value is very small for these three. And for the other, the p-value is not that small. And the coefficient is very small, which means they are not that important. So we only choose these three, PGM, 3PM, and FTM. So FGM means field goal made. That means how much you can point. 3-point made, that means how much you can shoot. And field goal made is the total free throw you made in the game. So they are the three most important features to rate a player. And for one player, we have these different game weights. So here is the official weights for all the games. As you can see, WTI is the weight of the I most recent games. And that means more recent games have higher weights. We denote WPI as the weight of the I toughest game. And the game with closer results have higher weights. And these are the official definition of WTI and WPI in equations. You can see if I is equal to 1, then the weight is 10. If I is larger than 10, the weight is just 1. And using these weights, and we get the sum of all the weighted results, we can know the rates for a single player. And here is just an example of some players. You can see that for Gordon Hayward, the time weighted rate is 11.73, and the results weighted is higher than the time weights. So the difference is 5. That means that is not a trivial number. That means it makes sense to make the different weights. And then we get the overall, which is the average between these two, to be the final rates for this single player. And for all the players, we got all the rates. We can finally go to the last step, which is the team construction. So the basic idea in here is given the optimal team model, which is one player from cluster 1, one from cluster 5, some from cluster 4, and some from cluster 9. Using this team model, we choose the players from the according clusters to maximize the total rates. We know the rates, right? And without exceeding the salary cap. So here is the final roster. You can see that here's the rates and here's the salary. If we add them up, it will not exceed the salary cap for the 2023 season. And here's the implementation on WNBA. And the first one is the COA score in the clustering. As you can see here, the number of clusters shows that 12 is the optimum one. But comparing to the hierarchical and COA score for the PCA data in NBA, this one is very small compared to that one. And the visualization also shows that the distance between the clusters are not that large. So we believe that this is caused by the lack of data in this league. Because it's a much smaller league, there are much smaller players, much less players, and much less games. So we don't have that amount of data as in the NBA. And here are the future work. So first is about the flexibility. So we think that we can give the decision maker options to adopt the actions recommended by the framework or not. So specifically, in some case, maybe when you choose the team models, in this case, we just choose the models from the one that is optimal. But maybe some manager, they prefer some other style of players. So maybe you should give them the rights to choose from that point. And for the small basketball leagues, we should apply different features reduction models. Maybe other than PCA, we can find something less aggressive than that. And for other sports, maybe like the soccer, the American football, or the hockey, or the cricket, we can adjust the feature types and clustering the methods, but other things may be just the same. For the playing style, and this is an important one because in these recent years, the playing style in NBA has changed a lot compared to 2000s or even 1980s. In this research, we have considered include a lot more data from 1980 we also have the data back then, but we think that the difference of the leaks now and then are too huge. It's too huge that we cannot think that we think maybe they will impact the decision maker today. So maybe we should give more recent inputs, more ways in training the neural network. Maybe that is one way to solve that. And then salary prediction. In this final roster, the salary is given. The salary is the salary of this specific of this player in the past year, not for the next year. So maybe the salary will change after this season, and we do not provide any salary prediction in our work. So in the future, maybe we can develop a machine learning framework to predict the player salary in the next year. And the last one is a user-friendly interface. By now, they are all very difficult to implement if the manager do not know much about computer, right? So maybe we should develop an application or website that can be used very easily and friendly for the team owners or managers. And here's the reference that we just mentioned, and thank you.
Thank you, Yuhao. This is an excellent talk.
Thank you.
So we'll take some questions.
Do I just
yeah,
and do I just reading or
yeah.
Okay.
So questions from here. Maybe it's best you come and ask the question here so that you are heard more.
Okay, so that.
Yeah, you stand next to Yuhao and ask the question. This is part of the recording.
Oh. Can you go to like my question is regarding the
you can just look
features, selection of the features.
Selection of the features.
Then when you pick the time when the elite players are being selected, remember the time 0.146?
Yeah.
That's result. I wanted to ask a question on the result.
Okay, sure. This one?
Yes.
So, yeah.
When you selected, we know how you got the elites their time. The other ones, how you sparsely separated them according to each clusters, because you were giving them did you the remaining time is now being assigned to them? Is that what you did?
That means all the remaining times are distributed equally to the players from these clusters. So maybe it's like one player from here, two players from here, but it doesn't matter. They all together they contribute to this much of times in total.
Oh, okay. I understand what you're saying. It's clear right now. Then the second question I wanted to ask is regarding when you were picking the features.
Yeah, picking the features.
When you selected you have 17 features.
Yeah.
And you at the end of the day went down to
13.
13.
13. Yeah.
Okay. Which method? Because I didn't get that.
We just use the PCA.
I know the PCA is classification and you're classifying them according to what?
The PCA is not for classification. The PCA here is to reduce the number of features. So we have the PCA. The PCA features is a composition of the old features. So we just add coefficients to the original features to get one PCA feature. And the coefficients is what we need in this case.
Okay.
Yeah, and that's why
that's a question because for you to select the 13, that's what I'm asking. Is there a selection criteria that you use? That was what I'm saying. Even if you use PCA in making the selection, there should be a selection, whether it's CV condition following this or something like that. I don't know.
Oh, you mean to select these 81 features?
You have 71 features.
Yeah.
And you reduce to 13.
Yes.
That's what I'm saying.
Okay, so over 90% of total variance. So total variance is the criteria here.
Okay.
So as more components you get, the more total expand variance we will have.
Okay.
But at some point that is good enough. We don't want
too much. Yeah.
Thank you. Thank you.
Okay. Okay, we'll take another question. Maybe.
So just go to your framework.
Yeah, sure.
Question about the framework.
Yeah.
Right. So in the last step 5, when you're doing the team construction,
yes,
you're making a recommendation, but how do you test whether your recommendation is accurate or not? what is your criteria for saying, okay, this is the final recommendation from me? How do you test it?
So you mean how do I optimize the results? Okay, so yeah. So maybe I should
Not
explain.
optimize, he's asking how do you test if your recommendation is
Oh,
correct?
how do I test if it's correct? So there are several things to test it. So just in this case, like let me get you the final roster. Yeah, for this one. So here are the final roster. Yeah, here's the final roster. And by the time that you get these results, there's no way to know whether they are very good at that time. But lucky for us, this paper was completed at the end of 2022. And now it's the beginning of 2024. So we know how they performance on the season 2023. And by now, this guy, Dylan Brooks, you can see the salary here is about 11 million, right? And this year he got 22 million. Yeah, that is how good that's how good he is. And this one, Anthony Simons, and originally they got 22 million. The salary is not going up because that is the highest one he can get for now. They have the salary cap for the single players also in NBA. And this guy is now the number one player in his team. And the original number one has just left the team, and now he's number one, and he's taking control of the whole team. That is not expected before. So maybe this comparison can tell you that this is a very solid team roster.
Wait a minute. When you're optimizing,
yeah,
then you're making a recommendation for what the roster should be.
Yeah.
So you can't test it against actual data because your recommendation for how the roster should be isn't a prediction about what they're doing. Right. So my point is what they're doing now is not necessarily optimal. Right?
Oh yeah. So we are not only
These
considering
are apples and oranges that you're comparing with just the last few sentences you said. You're comparing apples and oranges, right?
Yeah.
You want to. It's perfectly fine to come up with the roster as a suggestion of what the optimal roster would be. That's fine. But when you to use actual data to then make a claim that that's a prediction, I don't think is correct, because otherwise the roster you're coming up with isn't improving on reality, right? You're making a recommendation for a roster that is going to improve over what the teams are doing already.
Oh yeah.
So if you try to use it to test it against actual data of what they're doing, that doesn't make sense.
All right, I see the point here. So let me explain that. So for our work, the final roster here is like we made up the team. So like we can choose anyone that we want from the overall league. But that is actually not the case. I believe that's what you're pointing out, right? So if we are recommend a team for an actual team manager, we have to give the recommendation based on what they have right now in the team.
Well, there's a difference between a recommendation and a prediction.
Yeah.
So the advantage of what you've done is that you're using it to design essentially optimal teams, which is great, right? That's fantastic. But then to say that you're going to test whether your team is optimal or not by comparing it to actual data doesn't make sense, because a good test result there tells the team manager, oh, I'm doing the right thing anyway, right? So why do I need your recommendation?
Actually, Rodney, so it's basically the method is producing a set of players, right? It's a roster, right?
That's correct, yeah.
It's basically, so what Yuhao is saying that some of those players who we can see that were recommended by the system, they are basically being hired or their salary is either increasing a bit or decreasing a bit. So that's a way to kind of validate. So this is like it's a bit of a qualitative comparison in that sense.
No, it's confounding the difference to introduce two new terms. Essentially, the model is a normative model, right? So it's saying what ought to be. And then to validate it, you're trying to then turn it into a positive model about what it is to test it against actual data. You can't do that. That doesn't work. Right? These are two fundamentally different uses of the model.
Yeah. Yeah. So technically, like I don't think there's one way to actually validate if this is the best one we can get for the final
No,
roster under the salary cap. Like
the
technically,
only
we cannot do that.
the only way you can validate if it is a good outcome or not is if they act on your recommendation to implement that team, and then
Yes.
you look at the performance of the team. That's the only way you can do it.
Yes.
But the thing is like, this is what Yuhao is saying, that this was done more than a year ago, and what they have acted upon, that is having some of the overlaps with some of the players that were recommended by his method, right, Yuhao?
Yes. Yes. Like my point is that in my final roster, we have some like non-elite players. They were not that good, considering they have like so less salary before than now, right?
Yeah.
They were totally hit in the original team, but now someone also detected that they are good enough, and
Yeah,
they
but
are
what-
willing to pay more salaries to them.
But then you're still assuming that you're assuming essentially that the manager in the past was implementing an optimal team. There seems to be a logical mismatch here.
Okay,
Because-
yeah, something to think about. Thanks,
Yeah.
Rodney. Okay, you had another point, Rodney? Okay, great.
You need to make this team, let them play a season, then evaluate their results.
Yeah.
Because you're recommending a team, not just individual players.
Yes.
But you're using the salary of the player as a proxy to measure how good a team would hypothetically have performed, which is
Okay, so you guys, anything from?
Oh, that right. I see.
Come, say it here so it's more visible. Yes.
When we say about this one research, that is first before this speaking about this research published in the top journal, and is this a proof this the research is the correct and is the exactly that I believe about this. That then when we speaking about this some question just about just should be for this the increasing our knowledge about this the research, and another section about this recommendation that this research focus on this the data that is based on the data, and you know I'm working for the recommendation from the several years ago, but in this the real world is dependent the several conditions, several features for selecting for these the some players that really depend to the a lot of this the feature and out of this the data. At all, I believe this the research is so strong and proof this the published to the applied science and is the T1, D1 and the top journal. At all, thank you for this.
Okay, thank you. Okay, thank you, someone. And to add to this, I think, if not emphasized earlier that much, the future work is also application of this to some other sports that Yuhao is going to pursue. And also similar frameworks can be developed for other things such as recommendation or promotion in a workforce, where you look at the characteristics of the, so as players in a workforce, you have staff members, and some of them we have a performance management system. And how do you implement a just performance management system which is guided by AI. That's a very important thing, and that's something that can be pursued in future work by some sort of synthetic data or even some real data if it is available. But thank you so much.
Thank you, everyone.
Right. I'll just stop the recording, okay?
Yeah.
You can stop the recording.
I'll stop the recording here.
Yeah.
Stop the recording.